And so here I'm showing you a figure of the current best understanding of climate of the deep ocean. Is really, I'm showing deep ocean temperature, but climate of the past 60 million years of Earth history. And so on the x-axis here is time in millions of years. So we're here at 0 million years. We're just this little blip. And then on this y-axis is the oxygen isotope composition of benthic foraminifera, which is a bit of a mouthful, but they're these shells, these organisms that live in the deep ocean that have carbonate shells. And so scientists have drilled the ocean crust, or the sediments on the bottom of the ocean floor, and then reconstructed or measured the oxygen isotope composition of those little creatures to reconstruct the temperature at the time that they formed. And so we can create this kind of this curve of what we think deep ocean temperature was like through millions of years. And you can see that through this time period, Earth has gone through quite a bit, and that this current climate state that we're in is actually very different than the one that we experienced millions of years ago. It's actually one of the colder climate states in recent geologic history, where we didn't see ice sheets until about 30 million years ago. So this blip here is the start of ice sheets. But the periods of time that I'm most interested in are these periods of time up here. And what I find fascinating about this is that it's so warm. And so on this y-axis, you can see effectively what the temperature changes compared to modern. So this is something like 12 degrees Celsius warmer in the deep ocean than modern, or even more than 12 degrees Celsius. And what's important about this time period is that this is about the amount of warming that scientists predict that we could be headed towards. And so this star is approximately the temperature change that we can expect to witness under what's called representative concentrations pathway 8.5. And that's essentially business as usual greenhouse gas emissions. So if we continue to emit greenhouse gases at the same rate and increase our emissions at the same rate as we currently are, then we can expect to witness this much warming in the next century. And so this highlights this period of geologic time as a really key period to understand, because we can use it as an analog for future climate, and it can also be used to illustrate end member conditions. So this is the consistently warmest period of time in the past 60 million years. And I put this back up to remind myself to explain to you why I showed this goofy little alligator and palm tree earlier. So this time period called the early Eocene, we qualitatively knew was quite warm, because scientists in the 1980s, I believe, found evidence for palm trees and alligator fossils at really high latitudes. So even in the Arctic and places now like Greenland that's covered in an ice sheet, we found deposits of this age that have alligator fossils. So we know that it was quite warm, that it was a tropical forest at high latitudes. But the question is, how did it get to be that warm, and what did that mean in terms of other climate states, other aspects of the climate system during that time period? Like I said, the water that I'm really interested in studying doesn't exist anymore because it is evaporated 50 to 60 million years ago. And so we have to get a little bit more creative in what we use as a record for aridity. And so what I use in my research are soils, and these are one of the best geologic archives of ancient climate that we have. And this picture that I'm showing you here is of what's called the John Day Formation in eastern Oregon. And each of these stripes on this hill slope, each of these tilted stripes are an ancient soil, or is an ancient soil horizon. And so we can look at the minerals that form in each of these ancient soil horizons and start to understand the climate under which these soils formed, as their soils are just at the really, really thin surface of the earth. And so if it rains more, the soil's geochemistry will reflect that. If it's more arid, the geochemistry will also reflect that. And so we can go back and find places where these kind of ancient soil horizons exist from the time period that we're interested in, and look at the isotopes in these soils to understand the evolution. of something like aridity through geologic time. Okay, and more specifically, I use a mineral called calcite or calcium carbonate. So if I use those terms interchangeably, they're the same thing. And I look at the oxygen isotope composition and also the carbon isotope composition, which I did not explain but could later. And so this mineral looks something like this. It's kind of an unattractive mineral. It's a little blob of calcium carbonate, and then this is a picture of kind of what that carbonate looks like in an outcrop or in a rock, where this what's called a nodule of carbonate forms in place. And so we can go back and collect, or we can go out into the field and collect these soil carbonates. And what makes them useful is that they form in soil water. And so the isotopes of that mineral, the isotopes of the calcium carbonate, will record the isotopes of the water from which they grew. And they'll also record other information that I'm not going to go into a lot of detail about, but as you can see on this this diagram of CaCO3, there's one carbon isotope and 3 oxygen isotopes. So this carbon isotope can also tell us a lot about the vegetation that under which that soil formed. It can also tell us something about the concentration of atmospheric CO2 under which that soil formed. But I'm really interested in the relative proportion of these oxygen 16s versus oxygen 18s, again, because they can tell me about evaporation. Okay, so the method that I'm working on is actually fairly new. We are witnessing we're under a period where we're seeing increased precision in laboratory sciences, so we're able to measure increasingly small signals, and which means that we can finally go after big questions like how has aridity changed and how much has evaporation changed through geologic time. And so the question that I'm attempting to answer right now is how the oxygen isotopes of modern soil carbonates changes in modern environments. And so this axis here on the Y is increasing evaporation on the bottom and then decreasing aridity on the x-axis. So the hypothesis that I had when I started was that in modern soils, I would see less evaporation in soil water compared in these more humid areas, whereas in an arid place, I would see more evaporation. So something like desert regions would fall in this quadrant, and a soil that formed in a humid place would fall in this kind of quadrant. And so my strategy is to measure this in modern soils first, so that we can then use it, then we can apply what this tool, essentially it's called a proxy for aridity or evaporation in ancient soils. Okay, so the strategy that for this study that I'm going to show you the results from, I've collected modern soils from a range of environments, from arid to humid places, and then I measure their oxygen isotope composition and build this graph. So this is proxy development work, essentially. And so here's some pictures of some of the places that I've gone out and collected soils from in the past year. This was me in the Mojave Desert in August of 2020. So just a couple months ago, I went out to the Mojave Desert. It was about 106 degrees by 10 a.m. when we stopped doing our field work. So we got up bright and early to get out and collect these soils before the heat of the day. And it's always a good reminder. It's always kind of fun to do field work in really, really hot places when I'm trying to understand hothouse climates. It's a good reminder that it could be much hotter, probably was much hotter during the Eocene in this time period that I'm interested in, which is hard to imagine when it's 110 degrees. But here I am on this is a modern soil surface. This is me collecting the sample, and this is the soil pit that I dug with my field partner. And then here in this picture, I'm pointing at that beloved soil carbonate, which is, again, not the most distinct mineral, but it's kind of this white coating that's around the clast. And so this is what I was after. I actually took this clast home and put it in a bag and then started to analyze it. And here's some pictures from soil in Livermore, California. this is the Bay Area of San Francisco. And you can tell from this picture that this is a very different environment than the Mojave Desert. There's fresh green grass. This is, I think, December, so a little bit different time of year. There's water. I know these hills are all brown right now, but you can tell that this is not quite as dry of an environment as the Mojave Desert. And the soil looks a little different too. It's this kind of thick black soil with these small little nodules that I'm pointing to in here. And so this tells you something about, you can already tell that this environment is pretty different. There's more organic matter in the soil that's making it a darker color. And then I can also predict that the oxygen isotopes of this calcium carbonate is going to be pretty different. Like the prediction would be that these would be less, they would look less evaporated than the soil carbonates in the Mojave Desert, where it's pretty dry. And then this is kind of an in-between place that's close to where Headwaters is based out of. I went to Sierraville, California, again in December. You can tell because there's snow on the ground. And I didn't have to dig a soil pit here because there was this road cut, which was very convenient. So I drove up to this road cut and then logged the soil profile and collected. Again, here I'm pointing at that my favorite white mineral calcite that's in the soil. And so these are just kind of a snapshot of 3 of the environments that I've sampled. You can tell that they're pretty different environments and probably have different aridities in the modern. And so the goal is that I could use these to calibrate the past. Okay, so then once I have these soils, how do I measure their oxygen isotope composition? So as a reminder, here's the graph that I'm working on right now. I predicted that there would be a relationship in modern soils where I would see increasing evaporation of in the oxygen isotopes of modern soil carbonates in more arid places. And this kind of looks like it's true. So yes, it's true, but this relationship is probably more complicated. So it's certainly not a single line where we see continuous evolution with decreasing aridity. But instead, what we observe is that in these dry places, like these colors here correspond to where I collected the soil carbonate, where the key is on the right. Then these dry places like in Nevada, and this sample is from the Atacama Desert in Chile, which is one of the driest places on Earth. So over here, we definitely see that the soil waters formed under extremely evaporative conditions. And so we could use this to detect an extremely arid environment in the past. And then over here on the right-hand side, it does look like these soil carbonates that were collected in Texas and in Argentina, this sample is from Myanmar. These are forming under conditions that are not really evaporated. So this would look something like a humid climate. The in-between is where it gets complicated, and it certainly looks like there's more of a process threshold than a linear relationship, where there's some soils that are not evaporated at all, some soils that are extremely evaporated, and then a lot of soils that are in between. And so I think that this isn't a perfect proxy, but I think it will help us to it certainly can be used to detect aridity and certainly extremely arid environments in geologic past. So I'm not going to show you any results from the geologic record because I don't have them yet. So that will be the next task the next year, is to use this relationship that I've developed in modern soils to apply it to ancient soils that I've collected and understand how aridity has changed during ancient global warming events. And here I'm showing you a picture of early Eocene soils in Big Bend, Texas. And again, each of these colored bands, the white and the blue and the purple and this yellow, are different ancient soil horizons. And so you can collect soil carbonates up this section and hopefully produce a record of how aridity has changed through geologic time. So to sum this up, the geologic record offers a valuable perspective of climate change in hothouse worlds. I'm interested in the early Eocene because this is one of the time periods that we know is extremely warm, and there's a lot of carbon dioxide in the atmosphere. So we think that these time periods are good analogs for future warming. And soil carbonates are one of the few tools that we have to investigate those ancient climates, especially on land. So I showed you that we have a pretty good record of how temperature has changed through the deep ocean, but on land, the record can be more difficult to find. But soil carbonates are one of the few tools that we have to reconstruct ancient climate in deep time. And what I'm working on right now, and hopefully what you feel like you have an understanding of, is developing stable isotope tools we need to be able to interpret those archives that exist. Those rocks are out there and they know what the climate was like. It's just a matter of us figuring out how we can read the climate record from those rocks.